telling us about inference-time algorithms.
Thanks, Aram. Can you just tell me when do I end, just so I have a... Yeah. When do I end? Yes.
45 minutes.
OK. All right, good. So I'm going to tell a little bit about inference-time algorithms. And so I guess what I'm going to start with is to kind of tell you a story about like why I'm going to be interested about what I'm going to be interested in. And then really, I guess my excuses of what I'm going to be talking about is to kind of give you a couple of cute algorithmic tricks that I think are just maybe even more broadly useful than what I'm going to tell you. So I guess like somehow the story starts that maybe like starting somewhere in 2024, it's kind of progressively been the case that the kind of types of systems that are deployed are really like much less so a monolithic system and much more so like a kind of compound system. So in like, early 2024, this was really just kind of like integrating calls to other models, kind of tool calls. Like around 2025, like agentic systems became more and more kind of like widespread. And then I guess now we kind of really don't blink when we see these diagrams of sort of like scaffolds or workflows to do very complicated things. Like, I mean, this is basically the early version of Alethea, which was kind of one of these systems that was, I guess, an offshoot of the first IMO gold-achieving model by DeepMind. And now there's even these kinds of like harnesses which are meant to improve the harness that the model is using, so kind of self-learning harnesses. So inference-time algorithms are really maybe the simplest kind of incarnation of this, where the idea is that maybe you have kind of like one or multiple pre-trained models, and you kind of want to use them as subroutines, so you want to kind of call them as oracles, potentially expending more work at test time so you can kind of do something better at test time. So do something better could be get a kind of better quality answer. It could be sort of like, skewing or steering the answer towards something. And so maybe some kind of examples, I guess, so this is a little bit more concrete, are on the slide. Perhaps maybe the earliest sort of version which added this to the zeitgeist was, I guess this is a figure from the 01, which is, I guess, the first thinking model by OpenAI, where sort of the idea was that if you kind of allow the model to take progressively longer time thinking by sort of being trained on longer chains of thought, then maybe you can kind of increase the accuracy for the answers that it can answer, or maybe even the hardness of the questions that it can answer. Maybe a more pertinent example to diffusion models will be kind of solving inverse problems, where the idea is that your pre-trained model serves as a kind of oracle modeling the prior for your data, and then you want to sample from the posterior, giving some modeling assumption about what the kind of operation that acts on the prior is. So maybe here it's kind of in-painting, and then steering is kind of a popular thing in the sciences, where perhaps you have a pre-trained model that acts as a prior for molecules or something, and then you want to kind of steer it towards generating molecules that have certain properties. And okay, maybe from a kind of practical point of view, this is, clearly both a useful and a very general paradigm, because it sort of allows you to do a variety of things. So it allows you to incorporate new information at test time and sort of like still use the pre-trained model, but kind of add new information. You can kind of treat these pre-trained models as very powerful, very expressive priors, and it allows you to kind of trade off the amount of time that the model runs for sort of better quality answer. That could mean like better accuracy, solving harder questions, and so on and so forth. Maybe, I guess, like in this crowd and for what I'm going to talk today about, I think it's a very kind of natural playground for interesting theoretical questions, because in some sense what this means is that you kind of are using these pre-trained priors as oracles of sorts, albeit like most of the time the type of oracle you should think about are maybe kind of more powerful than the standard oracles that we like thinking about it. And oracles have a very, very kind of rich history in optimization and theoretical science when trying to understand the hardness of various questions. And there's kind of interesting problems here, both in terms of trying to understand what are reasonable modeling assumptions for these oracles, and then kind of subsequently interesting algorithmic questions around what can you do with these oracles, what are the most efficient algorithms you can use for this, and I'm going to tell you a little bit about that today. Okay, and in some sense, maybe another kind of appealing pitch here is that unlike other parts of like the training pipeline for kind of for big AI models, in some sense here the algorithmic design space is rather rich. It hasn't kind of settled quite as much as it has for pre-training, and it's not really clear it's so easy to kind of explore in a brute force way. So it's an interesting thing for theorists to think about. Okay, so today I'm going to tell you kind of two vignettes. One is going to be sort of around understanding propagations of error in the kind of oracle that you have for a pre-trained model, and in particular, like a kind of principled way to track this error propagation using something called backtracking. Strictly speaking, this is not going to be a strategy that's only useful, or maybe I won't even present it in the context of diffusion models, but actually, as Mole talked about yesterday, there's a way to kind of adapt this for discrete diffusion models. It's a kind of very generic strategy, and I'll say a little bit about that at the end. And then part two is going to be a little bit about kind of understanding the tractability landscape of a problem that's specific to diffusion models. So basically steering diffusion models when I kind of want to tilt the distribution that the diffusion model is specifying using like, some kind of simple reward. And as I said, like in both cases, there'll be some interesting kind of like little kind of algorithmic primitives that I think are useful even beyond these two settings. And I think they're kind of cute to know. Okay, so let me tell you about the first vignette. So this is going to be joint work with a bunch of people who may or may not be in the room, but they're certainly here. So Dhruv is a Miller Fellow here at Berkeley. He was a grad student at Berkeley, at MIT. Abhishek was a postdoc at MIT, now is an assistant professor in Georgia Tech. Donia is a student of Avram Blum who was visiting me during this project. Yuchen was my student who's now at Google Research. Ankur doesn't really need any introduction. And then Dylan Foster, who's a research scientist at Microsoft Research. Okay, so now let me kind of start putting some flesh, I guess, like on what I'm talking about. So I'm going to tell you a little bit about something which is called like the kind of generator-verifier approach to test time scaling. And the sort of general idea here with sort of like keeping things still kind of reasonably high level is the following. I'm going to imagine that the task that I'm trying to solve, I kind of get to solve with two oracles at my disposal, something like a generator and something like a verifier. I'm going to think for the sake of this vignette as the generator something like this. So it's a kind of machine which takes in some prompt. I'm going to think of this prompt as living in some space script X, and it outputs some response. I'm going to think of this response as a sequence of length capital H, where the elements lie in some set script A. And then there's also some kind of verifier that provides some kind of score for these answers. In fact, I'm going to look at a sort of maybe more finer-grained version of this verifier, which is sometimes called a process verifier, where the idea is that this object, so this like process verifier, rather than just scoring the full responses for the kind of final length H generated sequence, it can also give me scores for prefixes of the sequence. So maybe I kind of output the first element, A1, it can return something like, a score of how good it thinks it is. Maybe it thinks like, 0.1 is bad. Maybe I kind of try to regenerate the first element to some A1 prime, then maybe it says 0.8 and so on and so forth. And then I try to tack on another token with the generator and so on and so forth. So this is kind of clearly a more powerful sort of scoring mechanism, so you would expect to be able to do more with this. In fact, even if I sort of don't exactly tell you what these numerical scores are supposed to be denoting, like just sort of intuitively what this object can do for you, it gives you some kind of like look-ahead power. And in some sense, like, if you had perfect look-ahead power, you would expect to be able to solve some like, otherwise unsolvable problems. You can make this formal. I'm not going to kind of bother to this just here, but in some sense, you could imagine that maybe the prompt is like, some kind of SAT formula, and you're trying to figure out like a solution if it exists for this SAT formula. And if you had like a kind of perfect process verifier, which for any partial assignment of the values of the variables can tell you, is it going to lead to a complete, to like a sort of a satisfying assignment or not? Like you can just sort of do this very simple linear time algorithm where you just like try for the first variable. Is there a completing assignment with the first variable being true? If no, try with the first variable being false, and so on and so forth. And then in linear time, you're going to be able to find an assignment if one exists. So this is just all to say, like, if you had a perfect object of this kind, you would expect it to be kind of unreasonably powerful. So maybe you expect these objects to be imperfect. And in fact, like, as you might expect, most of the time these objects are going to be learned from data. So they're going to be imperfect by virtue of the fact that they're learned rather than kind of pre-designed. And the fact that like there's kind of these imperfections in these objects leads to a lot of kind of like literature going even like way back before the kind of modern language model era to try to figure out how to, on one hand, leverage the power that these objects have. On the other hand, kind of mitigate the error propagation from the fact that they're imperfect. This is like a non-extensive short list of some papers that try to do something or other in this vein. And at some point in time, starting with this paper with Eduardo, Yuchen, Ashe, frequently, and so on and so forth, I got kind of really interested in backtracking as a kind of potential strategy to mitigate errors. And I guess today what I'm going to ask is this question in some reasonable abstraction, which is to what degree can we avoid the error propagation and imperfect process verifiers, and what kind of does the algorithmic landscape look like if we're trying to kind of deal with errors in the process verifier. Okay. So let me now try to make the problem a little bit more precise, I guess, finally kind of tell you something that's precise enough to be able to tell you some math. So I'm going to imagine that, just to introduce some notation, I'm going to denote my kind of what I was calling the generator, and I'm going to call it a base language model. So this is kind of my pre-trained model. It's going to be a map which takes in a prompt in script X and outputs a distribution over completions of length h. My goal is going to be the following. I will have something which I'm going to call a tilt function. So this tilt function will take the prompt as well as a completion, and it's going to give me some value to this completion. So I'm going to imagine that this is something that is a non-negative output. And then my goal will be to sample from the tilted distribution. So the tilted distribution is the one in which I sort of sample from the distribution that's proportional to the base distribution pi ref multiplied by this tilt function tau. So what I want to do, in words, what this means is if tau puts more mass on this completion, I want to kind of upweight that in pi star. If it puts less mass, I want to downweight it. There's kind of many natural, by sort of instantiating tau to something, there's many natural problems that you could subsume here. So for instance, if you just imagine the tau is 0, 1, that will disallow some outputs and will not change the mass to the other. So this is a very easy way to frame constraint generation. There's other kind of natural things like Kale regularized optimization. So Kale regularized optimization just means perhaps you want to take some distribution which is close to pi ref, but tries to maximize the expectation of some reward. If you solve the corresponding variational problem, it gives you exactly this kind of tilted measure. So there's many kind of natural questions that people want to solve that fit in this kind of paradigm, and this is the general abstraction that I'm going to be interested in. Okay, and so this is basically the problem I'm going to want to solve. I still need to tell you what this process verifier does. I haven't really formally defined it. So I'm going to claim that the sort of right way to formalize what a process verifier does in this setting is the following object. Even though I'm borrowing notation from reinforcement learning, there will be no reinforcement learning in the talk, but the correct object is something which the notation calls it V because it kind of corresponds to a value function, but it just is the following object. This process verifier will take in the prompt as well as a prefix of some length, let's say little h. And what is the value it's going to give me? It's going to give me the expected value of tau, so my tilting function, conditioned on the prefix being fixed to a1 through a little h. So it's in some sense telling me how good this prefix is on expectation if I unroll according to the distribution pi ref, so the base distribution. Make sense? Okay. So I kind of hinted that maybe if you have a perfect process verifier, the problem that we want to solve should be very easy. And indeed, it's a very simple calculation to see that if you handed me this object v star exactly, so if I had if I had it in my hand perfectly, then there's a very easy kind of linear time algorithm to sample from the tilted distribution that we're interested in that does a very natural thing. So it will go token by token in the sequence. And if I'm trying to sample the token at position h, given the prefix up to h minus 1 that I've built up, what I'm going to do is I'm going to sample from the kind of re-weighted next token distribution, which is pi ref, weighted by v star tilt for the completion if I tack on that last token h. So this you can kind of easily sample from because it's a distribution just over one token. This is for the next token. And so you do this token by token until you complete the sequence. You can do this in time, which is linear in the sequence length times the size of the action space.
Your definition, is that capital H or little h?
Which one? There's both capitals and...
They're both capital and little?
This is capital, this is little. So this is the value of a prefix.
Also be capital.
Say that again?
On the left-hand side, the capital is also important, right? The capital.
On the left-hand side is little h. So I want to say this is the value function for a prefix. So for something that's of length little h, its value is basically the expectation if I unroll it to something that's of complete length, like of capital H.
No, what I mean is that the v star tilt presumably also depend on the capital H as well, right? If you change capital H, this function will change.
So I mean, the way that I define this is I'm trying to I guess, generate things that are of some length capital H. Like that's kind of fixed in the problem.
That's fixed in the
Yeah.
Capital H is the horizon. Small
That's
h
a
is
horizon.
the current.
Yeah. Okay, good. So that's a perfect process verifier. So now the question is, what if I do, I mean, somehow like maybe I kind of built this up a lot, but like now what do I do if I only have an approximate version of this object? So I don't have the exact process verifier. So maybe the first thing that you might want to convince yourself is if you just kind of do the naive thing and you don't do anything, you just run the same algorithm, this sort of like token-wise reweighting algorithm, I want to convince you that it's not a good idea. So if this like horizon length capital H grows, then like your error in the distribution that you produce is also going to grow, and like you should sort of think a little bit about something cleverer to do. It's not difficult to come up with many examples in which this is not a good strategy, but here's one easy example. So you could imagine that the base model is something very simple. It's a uniform distribution over 3 symbols, u, v, and w. Your tilt function is just basically the indicator for whether w is in the sequence. So you're trying to produce the uniform distribution over sequences which only contain u and v. Or put another way, it's a constrained sampling in which I'm disallowing w being in the sequence. So that's kind of the tilted distribution in this case. Is also easy to describe. And if you want to write down the kind of the true value function or the true process reward, it's also very easy to write down. It's exactly what's on the slide here. In fact, the sort of if you try to simulate what this kind of token level reweighting algorithm does, it has a very natural kind of graphical representation. Really what it does is what you would expect that it does. If you start with like the empty string, it's going to do the following with probability half append u, with probability half append v, and then continue with probability half it's again going to append u, with probability half it's going to append v. So kind of you can graphically imagine walking on this tree of prefixes where every time you go to like append u or v with probability half half. So now imagine that I don't have this exact value function. I have an approximate version of it, which is approximate in the sense that it's 1 plus minus epsilon multiplicatively close to it. And in this graphical representation, it's again kind of easier to track. In this graphical representation, what's going to happen is I'm going left, so I'm appending u with probability half plus epsilon. And I'm going right, so I'm appending v with probability half minus epsilon. So I'm biasing the moves by like an additive epsilon. And you can do like a kind of little calculation and to see that if you kind of ran this algorithm on this approximate value function, what's going to happen if the horizon length is capital H is that the total variation distance between the distribution that you want to produce, like pi star, and the distribution that you're going to end up producing is something that grows with the horizon. It's something like epsilon times square root of h. Okay. Okay, fine. I mean, you may or may not be convinced by this example. It's a very simple example, but that works in our favor. That just basically says that this strategy of kind of ignoring the fact that I have error in the value function is bad. Like even can manifest for relatively simple examples. We have like plenty of other examples in the paper which are more complicated. Okay, so what should you do? This kind of graphical intuition makes it maybe easy for me to motivate what we're going to end up doing. And so you can kind of think about what the standard autoregressive sampling does, like as you kind of keep appending tokens, as some kind of like walk down this tree of prefixes, where you always walk down the tree, and with some probability you append like the next symbol. This kind of action level reweighting does the same thing as well, but maybe with different probabilities. So it sort of reweighs with what probability you append like what symbol. The algorithm that I'm going to suggest is now kind of graphically natural. It's a random walk on this tree. So rather than just always going down on this tree, sometimes you're going to backtrack. So you're going to go up this tree with some probability. And if you set things up correctly, I'll show you what this random walk can do. OK. So here's the algorithm. I mean, it's really just like a very simple kind of one-line change to this action level reweighting algorithm. So it's going to basically do the following. It's, as I said, most naturally viewed as a random walk on this tree of prefixes. And it's basically going to do the following for sort of some technical reasons, which maybe for this crowd are natural, like to make the Markov chain lazy. With probability half, I'm just not going to do anything. I'm going to stay where I am. And then with the remaining probability half, I'm going to move to one of the 3 neighbors. So or like in this picture, 3 neighbors. Otherwise, there are going to be more neighbors. But either I'm going to move down, like into one of the children of the node, or I'm going to move up, which never happens when I'm doing either autoregressive or action level reweighting, with some suitable probabilities. And what are the suitable probabilities? So I'm going to move down to a child with the same probabilities as action level reweighting. So it's the reference distribution kind of upweighted by the imperfect process verifier v, and I would probability proportional to the imperfect verifier at the current state, so x and the prefix a1 through little h, I'm actually going to move up and erase the last token that I added. Okay, so I'm going to distribute the remaining probability mass half proportionally according to these probabilities. That's the sum total of the change of the algorithm. I see nods. That's always good. So that's the algorithm. So let me tell you what this algorithm does. So first, I need to tell you, this process verifier is imperfect. But of course, I have to kind of bound in what ways is it imperfect. So the guarantee that I'm going to need is the following. There's some relaxations of this guarantee that we can handle, but not perhaps very interesting ones. Basically, I'm going to say the following. Suppose that for every prompt x and for every prefix a1 through little h, the imperfect process verifier is multiplicatively 1 plus minus epsilon close to the correct one. So the ratio of v hat divided by v star is within 1 minus epsilon, 1 plus epsilon. And importantly, I'm going to assume that the process verifier is exactly correct, so it's equal to tau, if I'm at the end of the sequence. So there's no errors if I complete the sequence fully. There might be errors in all of the prefixes. This is basically, the motivation for this is that coming up with sort of like rewards for the outcome, like if I've generated the full sequence, is usually very easy. Coming up with rewards for kind of partial generations is harder, so maybe this is not so unreasonable as an assumption. Okay, this is in particular satisfied by this toy example that I showed you, and there's some relaxations that we can handle, perhaps not like the ones that you might want to handle. So I can say more if you're interested later. But okay, so what can we prove for this? So the form of the statement basically says the following. You give me some target accuracy delta that you're interested in. If I run this Markov chain, so this process that goes up and down the tree for sufficiently long, where sufficiently long is basically the most important, I guess, a parameter here is h squared, so quadratic in the length of the sequence, times this kind of closeness parameter 1 plus epsilon to the fourth times log of 1 over delta. I can guarantee for you that the total variation distance between sort of the distribution pi star and like pi hat conditioned on me like ending in a leaf in this tree is at most this accuracy parameter delta, and the probability that I'm going to be in a leaf in this tree, so the probability that I'm going to be like somewhere in the bottom of this tree, meaning like a completed sequence of length capital H, is not too small. So it's basically like about 1 over h. Okay, so how should you read this? So the way you should read this is this kind of greedy algorithm that always appends the next token reweighted with some probability, amplified the error as the horizon length gets longer. What this tells you is that if you are in this situation, so if you have approximate process like verifiers, and at the end, like at the leaves, the reward is the correct one, you can trade off runtime for better quality of the answer. So if you allow me to run longer, if I run this Markov chain longer, I can kind of be as close as you like me to be to the correct distribution at the expense of more runtime. So this is basically some way to, I guess, like formalize this intuition of test time scaling that you should be able to trade off more runtime for a better quality answer. Yes, Jianfeng?
So if we think about the analogy with diffusion, right, so that diffusion, the gradient of the value is kind of like control, right? So that in the diffusion context, the error is like in L2 of the gradient of V.
Yeah.
Can we like relax the assumption on that level, like L2 error, and so still get something?
So not really. Maybe the best analog to what you're asking is you would like this error to be on average with a1 through little h sampled from pi ref. That, in fact, provably does not work. Like, it's just not enough. If, for some reason, you had on average error according to pi tilt, like so the tilted distribution, then you can prove the same thing. But then it's a little bit questionable why you might expect that the errors are sort of good on average with respect to the target distribution rather than the reference distribution.
So the reason is that you need some coverage of the...
At bare minimum, but yeah, I mean, there's like a query complexity. But intuitively, yes, the coverage is different with respect to pi ref and pi tilt, and that's a problem, yeah. Was there any other question? Yes, sure.
So what happens if epsilon equal to 0? So in that case,
Yeah.
you still require quadratic runtime, but in fact,
That's correct, because this algorithm will go up and down anyway. In fact, if epsilon really goes to 0, what this algorithm is going to do is it's going to move one level up with probability half and to one of the children like with total probability half. So it's really just a drunkard's walk, like you go up and down probability
in
half.
this case, so if epsilon is too small, so this algorithm is not optimal. Because the epsilon
Sure,
is zero,
yes, sure,
we
sure,
should just,
sure. Yeah, sure. If you really have perfect answers, then you should not be running this algorithm. If you want something that smoothly trades off between linear when epsilon is equal to 0, maybe there is something, I don't know. This is definitely not it.
But is it because you are hard coding the 1/2 probability in your like what's your algorithm?
No, it's not really that. Like, so the half, so this half can kind of be removed. This is just for kind of technical reasons. You can shrink it as close to, just bigger than 0 as you like. Really, the probability is, the problem is, I mean, in a sense, like the main problem is that if you even forget about that, like you move up or down just with probability half, and you want something like momentum. If you had something where you have a tendency to move in the same direction and not switch the direction, that would give you something closer to linear. There is something you can do. There's like a kind of momentum-like version of this algorithm, but I don't think it like drops all the way down to linear, like if epsilon goes to 0. But there is something you can do.
I mean, intuitively, I would think that the backtracking probability should be proportional to the epsilon, the error.
Maybe. So I guess I don't know a Markov chain that quite behaves like that. But maybe.
I'm saying
Yeah.
the algorithm.
This is fair. Yeah. I mean, if you have 0 errors, you would just want to go forward. I think basically to make the stationary distribution work out, you still have to kind of, I guess, at least ensure that the stationary distribution is the one that you like. There's another question. Okay. Good. All right, so maybe just to say one sentence. I mean, like basically the intuition is that really what we've set up here is some like, random walk on an undirected graph, which happens to be this prefix tree with some suitably chosen weights on the edges. The stationary distribution, it's a simple calculation, is such that the relative proportions of the leaves are exactly the correct ones. So basically, if you actually reach stationarity, then the sort of relative probability that you find yourself in a leaf follows exactly the weights of pi tilt, like of the tilted distribution, pi tilt. And then this kind of h-squared dependence comes from the fact that, and maybe as I said, like it's a kind of diffusive behavior. You go up and down with probability half, so it's a kind of drunkard's walk type of behavior. Okay. So maybe I should say like the kind of inspiration for this algorithm actually goes way back. Like there's a very, very kind of classical paper due to Sinclair and Jerem in which they were trying to figure out how to sort of reduce the or like how to understand the relative complexity of approximate counting and approximate sampling. And the kind of main tool in the reduction is a sort of some special case of this algorithm that we have here.
Actually, they have an accelerated version.
They do, yes, yes.
So using lifted version.
In fact, I will maybe like say something in a bit, yes. So in fact, yes, there's a follow-up version in which they do something like momentum, which works if epsilon is sufficiently small and gets some kind of speed up. Maybe just like, let me say some subsequent developments after this paper. So maybe the sort of the first question you might ask, is this kind of h-squared behavior inherent? I mean, it's kind of clear where this comes in this algorithm, but maybe it's not, maybe there's a kind of clever algorithm that can do it. It turns out that the answer is no. There's a kind of beautiful paper by Noah, who I guess I don't see, Dhruv and Ankur, in which they proved that some kind of, if in some suitably formalized way, there's a kind of h-squared query complexity to, in the sort of full generality of the theorem that we have here. In a sense, like maybe you might want to say there should be some kind of variance in which rather than going up and down this tree, sort of reminiscent of how you kind of go up and down in temperatures in kind of MCMC when you do simulated tempering, perhaps there's something that kind of always goes down in temperatures. Maybe the first algorithm that you might think to do this is something like sequential Monte Carlo. In fact, like there are variants that sort of work in the similar setup in which we're interested in that are inspired by SMC. There's kind of two papers here. One is by Yiping Lu and a student, and the other one is again by kind of people in the room. So Noah, Drew, Fan, and a bunch of their collaborators, in which they kind of adapt some kind of SMC-like algorithm. I mean, due to this kind of query lower bound, it's indeed the case that also this algorithm in general also pays h-squared kind of total query count. And then, Mole had like a very nice talk yesterday. So this kind of strategy, though I presented it here for autoregressive models, you could sort of think about how to adapt it to diffusion models. And there is like some version that naturally fits kind of mask diffusion models in which you mask and remask this sort of in a similar way to how we backtrack in this autoregressive version. Though there's kind of a lot of interesting questions here in terms of like how much can it be parallelized and can you actually kind of beat this h-squared dependence in terms of kind of parallel runtime. So there's kind of lots of interesting questions here too. Think about. Okay, so maybe let me just do a little bit of kind of outlook on some sort of fuzzier questions that I think might be interesting here. So in some sense, like I think there probably will be much more kind of parallels and sort of adaptations of techniques in MCMC that might be useful for inference-time algorithms. So just that's maybe the kind of one broad question. In terms of kind of like modeling, and maybe the sort of, you could quibble with the assumptions that we have around like, what does it mean to have an imperfect process verifier? And in some sense, like the better models get, the harder it becomes to think about like how we should even model these oracles. There's certainly like a lot of discussion around this in kind of LLM land. So maybe here what I have a screenshot of is there was like a really nice bit in Tim Gowers' reflection after the unit distance problem, in which he has a kind of this, I don't know, like nice intuition that maybe we can think about the power of LLMs in terms of kind of something like a hint complexity or something, like how many hints need to be given to it until it can solve a problem. But maybe sort of like most broadly, like the question is, what are reasonable assumptions for how we can think about like modeling these now very powerful oracles? And then another sort of like recent obsession of mine, which maybe I will say something very fuzzy now. Perhaps by next time you hear me talk, it'll be less fuzzy. In some sense, like there's this kind of question about the strategy that we did ourselves by making the model backtrack by an algorithm that we prescribed. You could sort of imagine that the model can do on its own. And in fact, like you could sort of make the same argument for any of these kind of like scaffolds or harnesses that people write, in which you tell the model like, oh, like generate some candidate solution, try to fix it, verify it. Like in some sense, like there's something weird about having models that are so powerful that can solve like incredibly complicated math problems, but you need to tell it that the reasonable sort of workflow is that it should generate a couple of solutions, verify them occasionally, and then sort of revise them in some way. And there's like a kind of question of like why, like what kind of extra benefit is gained by these harnesses, and why couldn't the model just kind of do it on their own? Are there computational sort of like benefits? Are there sort of like error correction benefits? So there's like a kind of question about what is the extra power that's conferred by harnesses relative to just like the model on its own. Okay. That's my first vignette. Maybe I'll pause here, see if there's any questions, and then I'll switch gears. Hadi.
The complexity of finding this value function, or have you considered?
So this is here an assumption in the sense like we don't like that's kind of part of the input to the problem. The way that you would do it like usually in practice is by doing some kind of like fitting a value function on Monte Carlo rollouts. Like the way that it's defined, like the ideal one, it looks like some expectation. You can do some Monte Carlo rollouts, like fit something. There's some clear mismatches. So for instance here, I need a multiplicative guarantee of closeness. That would give you an additive guarantee. There's many kind of mismatches, but generally speaking, this is how you would train like a process. All right, good. So let me talk about the second part. So the second part will be more kind of explicitly about diffusion models. And it's again going to have like one algorithmic trick that I want you to take away from it. It's joint work with Dhruv and Ankur. I mean, this is a very short one-slide introduction to diffusion models, but you've seen the slide umpteen million times for this workshop, so I don't feel too guilty doing this. So the general idea of diffusion models is like, you have some data distribution, you apply some noising process, and then like, the way that a diffusion model works is you learn some kind of object, which is the score function, which is the gradient with respect to the input of the log density for kind of applications of convolutions or the Ornstein-Uhlenbeck process of the base distribution. And if you have this object, then you can kind of run this as the in reverse, and that gives you samples from the data distribution. So really the kind of only thing that's going to change from the previous section to this section is in some sense you can still ask basically the same question. I'm going to have some base distribution, but now, rather than this base distribution given by an autoregressive model in which I have sort of like a way to query the distribution over the next token, it's going to be given to me through another oracle. It's going to be given to me through a diffusion model, which just means that the way that I have access to this base distribution is I can apply some kind of noising process. So maybe just to fix some notation, you can apply Ornstein-Uhlenbeck, and then I can query the score after applying Ornstein-Uhlenbeck for arbitrary amounts of noise at like inputs x. And now the goal will be exactly the same one as before. I'm going to have some reward function, and I'm going to want to sample from the tilted distribution in which I kind of upweigh the base distribution that's now given to me through another oracle by sort of the exponential of this reward. Okay, and now the question I'm going to ask here is like less about error propagation. I'm just going to ask, when is this problem even tractable? For what rewards R can I sample efficiently from this distribution, given the access to this kind of oracle for the base distribution? Okay, in fact, even for very simple rewards R, it'll turn out that the sort of landscape here is kind of non-trivial. Okay, so maybe let me just sort of say, again, things that people in this crowd will know very easily. I just really need like maybe 2 mentions to sort of relevant prior work. So by now we kind of know if you didn't care about tilting the distribution, if you just wanted to sample from the base distribution, this kind of score oracle is very powerful, meaning that like, there's an efficient algorithm with a very small kind of number of queries, which I guess like returns samples which are close to your kind of intended distribution in multiple different notions of distance, let's say for the sake of the Stoch in Wasserstein distance. And the algorithm is also kind of the usual one, the one you might expect. It's basically you take the reverse stochastic differential equation, you discretize it with some appropriate step size. In terms of sampling from a tilted distribution, basically before our work, like in the kind of really the only work and maybe what served as the main inspiration for what we did was there's this very nice paper by Juan Bruna and Jijun Han in which they were kind of interested in inverse problems specifically with sort of linear measurements, and they were correspondingly focusing on rewards that are quadratic. So rewards that look like this, it's minus the value of some quadratic function, so minus 1 over sigma squared times ax minus b squared. The reason they were interested in this, you can think about A as a kind of measurement operator, and then sampling from the tilted distribution just means sampling from a posterior distribution over possible sort of x's from which your noisy measurement came from. And then sigma is basically the amount of noise that's being added. And basically what they show is that if you have sufficiently small sigma, so kind of the signal to noise ratio in this language, if it's sort of small enough, then this problem is tractable. And they also show that if the reward is a kind of arbitrary quadratic, then this problem is NP-hard by sort of a simple reduction to Ising models. So that reduction is just very simple to see. We're making no assumptions on the prior, so you can just imagine that the prior is just a mixture over little peaks over the discrete hypercube, and then if you allow tilting by the exponential of a quadratic, that's just literally sampled from an Ising model with an arbitrary sort of interaction weight, so there's no hope that this model is going to be doable.
You mean sigma large?
Say again?
Do you actually mean sigma small?
Sigma small, yes. Yes. Because if sigma is small, this quadratic ends up dominating more, then this is very log concave, so it becomes easier to sample from.
Sigma is large. The operator norm of that matrix over sigma is very small, and that's also good.
That's fair. That's also fair. Both regimes eventually become easy. That's right.
Sorry,
Yes.
I don't see the Ising model connection here. So this is a continuous case, right? X is
So,
under height.
Yes, yes. So I maybe, okay, this is going to be like a tangent, but okay, let me say it anyway. It's like your prior can be anything for the sort of problem that I'm interested in. So I'm saying, so imagine that your prior is basically a mixture of like very sort of sharp, like very small variance Gaussians over the vertices of the hypercube.
Oh,
Then I'm trying to sample from this tilt, like, and then basically it's almost an Ising model. Okay, good. So let me tell you what can be said when you sort of try to zero in a little bit more on like what kinds of rewards are sampleable, even if you focus on relatively simple rewards. So actually, it turns out that even if your reward is a rank 1 negative semi-definite quadratic, this problem is already hard. Like, so basically this Ising model reduction will kind of tell you that arbitrary quadratics are hard. In fact, even rank 1 negative definite quadratics are hard. And I'm kind of ordering them in some order which might look a little bit strange, but you'll see why. The other result that I can tell you is that if this reward happens to be linear, in fact, it turns out that sampling is tractable. And this is a kind of very simple result that will end up being quite useful. The third result is the following. If the reward is convex and low dimensional, meaning that it has the form that it's equal to f of Lx, where L is some matrix which is k by d, so it's basically projecting the d-dimensional input into something that's k-dimensional, and f is like convex and nice, whatever, like Lipschitz, then this is also kind of tractable in some fixed parameter sense, meaning like if k is small, then the algorithm is efficient, or meaning that you can get some algorithm which is polynomial in the ambient dimension, and like exponential in k only. Okay, so if you have some nice enough low-dimensional structure, then things are good. In particular, for this last result, if you take f to just be the L2 norm squared, then you basically get a low-rank positive definite quadratic. So that just also kind of as a consequence of this, low-rank positive definite quadratics are easy. Low-rank, even rank 1 negative definite quadratics, as it turns out, are not. Okay. So the theorem 1, I'm actually not even going to tell you. It's not that interesting. It's a very easy reduction. Let me tell you about theorem 2, which looks kind of surprisingly simple. In fact, the proof is very, very easy. But as it'll turn out, the algorithmic component that it gives is very, very nice. So the sum total of the reason why this theorem holds is the following simple identity. It basically says the following. Let me denote the tilted distribution by this linear tilt in a direction v as pxv. It turns out that I can write down the score for this distribution in a closed form sort of way in terms of the score of the original distribution. So the score of the tilted distribution at some position x is basically the score of the base distribution and some affine shift of the point x, and plus some expression that just depends on v. I claim this is just enough to actually just get the statement of the theorem, because now you have basically, even in closed form, you can express the score at any point you like in terms of the score of the base distribution, which you have access to. Then you can just run the standard machinery for sampling, if you have access to the score, and that's basically it. You just get theorem 2 for free after this identity. Okay, where does this identity come from? I'm not really going to write it out. It's an identity, so how complicated? Really, it's just you can just write it out. But basically, the idea is that when you write down the expression for the convolution with some amount sigma, you're going to get something that looks like an exponential of a quadratic, and then you're sort of appending, you're multiplying by the exponential of a linear thing. You can kind of complete the squares and sort of absorb it into the kind of Gaussian kernel, which kind of affects you by a shift, which is, I guess, what manifests here. And you sort of complete the square, and that's more or less what happens. Yes, Singho?
And if you have score errors?
This is completely error-free. What happens with score errors is an open question. Yes?
The issue with that idea is that, let's say the x is a typical point of the p sigma noising. The x plus the sigma over root 1
yes.
minus sigma, as sigma goes to 1,
yes.
that new point you're trying to evaluate at could be way in the tails of your base diffusion. And that's kind of what makes it hard to apply this idea with only, say, epsilon accurate score error.
That's right. I think it's even stronger than that. In some sense, if you can show anything that's just better than just doing rejections, you get some rate from just rejection sampling. Anything that's sort of better than just rejection sampling is open as far as I know.
So in some sense, you also need the average error for the tilted.
If you had that magically, then yeah, it's the usual coverage problem. In some sense, if I know where I'm tilting and I have a guarantee that the error is small where I'm tilting, I'd be fine. But why would you have that guarantee? So, okay, good. So as it turns out, this this result about convex low-dimensional things somehow follows with a little bit of work from just this linear case, somewhat surprisingly. So this is why I said this kind of linear tilt, even though it's sort of deceptively simple, it's a very useful primitive. And basically the idea is the following. I'm just going to tell you briefly what the idea is. Suppose you were somehow lucky and the reward that you wanted to tilt by had the special form of a log sum exp expression. So if it looks like a log of a sum of e to the something linear vi dot x, it turns out that, it's very easy to see that e to the r of x for this expression looks like a sort of a mixture of linear tilts. And we know how to do linear tilts, so that's all good. In fact, the reason why you would think of this is by some kind of analogy to the log Laplace transform. But okay, so for these special kind of r's, we can reduce the problem to sampling from just linear tilts. And then you can kind of prove some sort of almost universal approximation theorem. So you can sort of say that if I have a low-dimensional convex reward, I can't quite approximate it with something that looks like this kind of log sum exp expression, but I can basically kind of provide a sufficiently fine upper envelope so that I can fix the gap between them with some rejection sampling. And if you kind of stitch all of these two things together, then you get kind of the runtime that's in the theorem statement. So it's a kind of reduction to the linear primitive case. I mean, maybe just a sentence for this observation. Why would you expect something like this? I mean, you can write any convex function as like maximum, like a max of a bunch of like linear functions. The log sum is kind of like a soft max. There's no temperature parameter, which is why you can't quite universally approximate it. So you can just do kind of an upper envelope. But OK, it turns out that the rejection sampling step kind of takes care of that. OK. Good. So maybe let me just wrap up with some remarks. In some sense, what we're trying to do here is trace out like what types of rewards are easy, what types of rewards are hard. You might say like, OK, maybe there's some like special cases for the quadratic case that are easy. So maybe like diagonal, like quadratics are easy. Actually, it turns out that like it's just diagonal tilts are as hard as the general case because in some sense, like diffusion models are kind of rotationally equivariant. Like so, you can. I mean, this is maybe just in the interest of time. Like this is sort of the sketch of it, but you can. Let me just say you can just reduce the diagonal case to the general case. So that doesn't help. There's also something else that you might ask, which is like, in some sense, what is the sort of motivation behind this kind of exponential tilting? Well, you want to upweigh certain points and downweigh certain things. Like, but why upweigh them in this particular way by multiplication? In fact, like maybe as I hinted before, this sort of exponential tilting is basically the solution to some kind of variational problem, which sort of says, I want to be close in KL to some base distribution subject to, and I also want to make the expected reward rather large. But like, why be close in KL? You could say, like, I could be close in some other notion of distance, perhaps like Wasserstein distance or something. And it turns out that if you sort of make this change around like what notion of distance are you interested in, the tractability of the problem changes rather completely. So for instance, if you take Wasserstein distance, as it turns out, you can solve this like variational problem, and you can sample from the solution to this variational problem for basically any concave reward. So this is very different than what you get for KL. So maybe that's a kind of good place to pause, and so maybe some outlook for some interesting questions. So basically, we were interested here in very simple rewards because we don't really understand what happens even for very simple rewards. Of course, like basically both figuring out more complicated rewards and sort of understanding what happens when there's some joint structure between the base distribution and the reward that we're interested in is kind of wide open. There's no kind of, as Singhal already hinted, there's no kind of error analysis here. So basically being able to figure out what happens when you have imperfect scores is also very much kind of on the table. And then perhaps kind of the most open-ended thing is just sort of the remark from the last slide. In some sense, like, there's choices to pick from when you're trying to tilt your base distribution in terms of which metric you're interested in. It's not entirely clear what makes a metric sort of the right metric, both in terms of sort of the application domain and in terms of the tractability of the problem. So kind of understanding in which situations, which metrics are interesting, and kind of correspondingly designing algorithms is just like broadly an open question. Okay, that's kind of all I have to say. Here's the references for the papers. And thank you for the attention. Hadi.
So my question is that is there any link between distribution tuning and constraint optimization? Can we design a barrier function and do the same thing that the convex optimization people do for sampling, not for
I mean, possibly, right? Like, in some sense, you can view these distributions as a solution to some kind of variational problem. It's an optimization problem in the space of measures. So in principle, like, if you could come up with like a better algorithm that just sort of tackles this like framing of the question, it's just the same. Like, so I think the answer is like probably yes. Like, but yeah.
Okay. That's
Right? Thanks, everybody.
11 o'clock?
11:15.
Go for it.
11 o'clock.